The information presented in this video is strictly for educational and entertainment purposes only and does not constitute professional legal, financial, insurance, or automotive advice. While we explore the historical trends, potential outcomes, and mechanical capabilities of modern vehicle safety systems, you must remember that no technology can replace a fully attentive and responsible human driver. Driving inherently involves substantial risk. The case studies and statistical analyses discussed herein are based on aggregate national data and may not reflect individual circumstances or specific vehicular performance in every isolated scenario. Viewers are strongly advised to conduct their own thorough due diligence, consult their vehicle manufacturer guidelines, and speak with licensed insurance agents or legal professionals regarding how automotive safety features impact their personal liability, insurance premiums, and overall road safety. Do not attempt to intentionally test or recreate the engagement of emergency safety systems on public roads. Your safety and the safety of those around you remain solely your responsibility at all times. Imagine you are hurtling down Interstate 95 at 75 miles per hour. It is a rainy Tuesday evening in November. The asphalt is slick, reflecting the blinding glare of halogen and LED headlights from the oncoming traffic. Inside your cabin, it is quiet, climate-controlled, and deceptively peaceful. You are encased in 2 tons of steel, glass, and aluminum. Ahead of you, a tractor-trailer suddenly jackknifes, its air brakes locking up with a catastrophic shriek that cuts through the white noise of the storm. In a vehicle manufactured just 20 years ago, your reaction time, which averages 1.5 seconds for a completely unimpaired driver, would dictate your survival. You would slam on the brakes, your wheels would likely lock, your steering column would become entirely unresponsive, and physics would take over. The sheer kinetic energy of your vehicle would be transferred entirely into the crumple zones, and potentially into the passenger cabin. But you are not in a vehicle from 2 decades ago. Before your foot even twitches toward the brake pedal, a hidden network of millimeter-wave radar sensors hidden behind your front grille has already measured the rapidly decreasing distance between your bumper and the trailer. A stereoscopic camera mounted behind your rearview mirror has processed the visual data, recognizing the unnatural angle of the truck. In a fraction of a millisecond, the vehicle's electronic control unit calculates the precise braking force required for each individual wheel to maximize deceleration without losing traction on the wet pavement. Your seatbelt pretensions, pulling you firmly against the seat. The brake lines are pre-charged with hydraulic fluid, and before your conscious mind has fully registered the impending disaster, your car has already begun to aggressively brake on your behalf. You stop with 3 feet to spare. You breathe. You live. This is not a scene from a science fiction film. This is the invisible, ubiquitous reality of modern automotive transportation in the United States today. Yet, here is the shocking paradox that the automotive industry rarely discusses openly in their polished marketing campaigns. Despite the integration of automatic emergency braking, lane departure warnings, blind spot monitoring, and adaptive cruise control becoming standard equipment on millions of new vehicles rolling off assembly lines in Detroit and abroad, traffic fatalities in the United States have recently seen alarming spikes, reaching numbers we have not witnessed in over a decade. How is it mathematically possible that we are driving the safest, most technologically advanced machines ever conceived by human engineering, yet the roads feel more dangerous than ever? Are these invisible electronic safety nets actually lulling us into a false sense of security, creating a documented psychological phenomenon known as risk compensation, where drivers subconsciously take greater risks because they believe the car will simply save them from their own mistakes? We are going to examine the stark contrast between the laboratory capabilities of safety technology and the unpredictable, chaotic reality of the American highway system. We will dissect the granular data, analyze the historical trends of highway infrastructure, and expose the absolute truth about what happens when human psychology collides with cutting-edge artificial intelligence at highway speeds. By the end of this comprehensive masterclass, you will possess a profound, expert-level understanding of exactly how the modern safety features equipped in your vehicle actually operate, and more importantly, where their absolute limitations lie. This is not a superficial overview of dashboard warning lights or a reading of an owner's manual. We are going to meticulously dismantle the complex architecture of advanced driver assistance systems, commonly referred to as ADAS throughout the industry. You will understand the crucial life-saving difference between passive safety systems, which are designed entirely to mitigate bodily damage after a collision has already occurred, and active safety systems, which are constantly intervening in the background to prevent the collision from happening in the first place. For the American consumer, navigating the current automotive market can feel like walking through a minefield of confusing acronyms and proprietary corporate jargon. Dealerships will throw terms around casually, presenting these technologies as impenetrable shields that guarantee an accident-free commute. We are going to cut through the corporate sales pitches and rely strictly on engineering facts and independent testing case studies. You will learn exactly how camera-based lane-keeping systems can be completely blinded by low-hanging sun glare in the early morning, and why highly advanced radar systems can critically struggle to identify stationary objects, like stalled vehicles or debris in your lane, when you are traveling at high interstate speeds. Understanding these specific, documented vulnerabilities is not just an academic exercise. It is actionable, pragmatic knowledge that could quite literally prevent a catastrophic rear-end collision the next time you merge onto a congested freeway. Furthermore, we are going to dive deep into the complex financial ecosystem that surrounds these technologies. You will discover the intricate relationship between the sophisticated safety systems installed in your vehicle and the exact premiums you pay to your auto insurance provider. We will look at extensive historical trends and repair industry data that reveal why minor fender benders, which used to cost a few $100s to fix at a local body shop, are now resulting in staggering repair bills exceeding thousands of dollars simply because a minor bumper impact destroyed highly calibrated, specialized sensors that require proprietary software to realign. You will learn how to audit your own vehicle's specific technological capabilities, how to properly maintain these sensitive electronic arrays to ensure they function flawlessly when you need them most, and how to adapt your personal driving habits to work seamlessly with, rather than against, the rapid algorithmic decisions your car is making hundreds of times per second. This deep dive is specifically designed to transform you from a passive passenger sitting behind the steering wheel into an informed, hyper-aware director of your vehicle's ultimate safety potential. We will systematically explore the unforgiving physics of crash dynamics, the deeply ingrained psychology of driver inattention and distraction, and the astonishing, continually evolving engineering solutions that are currently rewriting the fundamental rules of the road. Whether you commute 10 miles a day in stop-and-go suburban traffic or traverse the country on massive cross-country road trips, the insights and operational breakdowns detailed in this masterclass will fundamentally alter the way you view the machine sitting in your driveway, giving you the critical foundational knowledge required to navigate the modern transportation landscape with confidence and authority. To understand the sheer magnitude of this technological shift, we must first look at the tip of the spear in accident mitigation. We begin with the foundational architecture of forward collision warning, integrated seamlessly with automatic emergency braking. For decades, the automotive industry relied solely on the physical reflexes of the human operator to initiate the deceleration sequence. Today, as we navigate the increasingly congested American roadways in 2026, the vehicle itself has become an active, participatory observer in the driving experience. This transition is made possible through a highly sophisticated engineering concept known as sensor fusion. Sensor fusion is the continuous, real-time collaboration between completely different types of hardware, primarily millimeter-wave radar modules and high-definition stereoscopic cameras, working together to build a three-dimensional map of the environment ahead of your front bumper. Consider the radar component first. Behind the plastic emblem on the grille of almost every modern vehicle sits a radar emitter operating at an incredibly high frequency, typically around 77 GHz. This device fires electromagnetic waves forward at the speed of light. When these waves strike a solid physical object like the metallic rear liftgate of the crossover utility vehicle stopped in your lane, they bounce back to the sensor. By measuring the microscopic delay in the return signal, the onboard computer calculates the exact distance to the target. More importantly, by analyzing the change in frequency of the returning waves based on the Doppler effect, the computer determines the precise relative speed at which the gap between your two vehicles is closing. This calculation is not performed once. It is executed hundreds of times every single second, creating an unbroken stream of high-fidelity spatial data that a human brain simply could not process with equivalent speed or accuracy. However, radar has distinct limitations. While it excels at detecting large metallic objects piercing through dense fog or heavy rain, it struggles to identify the specific nature of those objects. To the radar, a stalled passenger car and a large metallic street sign hovering over a sharp curve might return highly similar signatures. This is exactly where the stereoscopic camera system, typically mounted high on the windshield behind the rearview mirror, steps in to fill the sensory void. Operating at high frame rates, these optical sensors utilize advanced image recognition algorithms trained on millions of miles of driving data. The camera can differentiate between a vehicle, a pedestrian, a cyclist, or a completely harmless shadow cast by a highway overpass. When the radar detects a rapidly approaching obstacle, and the camera visually confirms that the obstacle is indeed another vehicle occupying your lane of travel, the sensor fusion matrix achieves a positive lock. Imagine a scenario playing out right now for a driver named David, commuting on Interstate 35 through Austin, Texas in the year 2026. Traffic is flowing relatively smoothly at 65 miles per hour. David glances down at his center console for roughly 2 seconds to adjust the climate control. In automotive engineering terms, a 2-second distraction at 65 miles per hour means the vehicle has traveled blindly for nearly 200 feet. Ahead of him, traffic comes to an abrupt, violent halt due to a sudden lane closure. David is looking down, but his vehicle is looking forward. The 77 GHz radar detects the stationary mass. The optical camera confirms the brake lights of the cars ahead. The vehicle's electronic control unit recognizes an imminent collision trajectory. Before David even lifts his eyes from the dashboard, a complex mechanical symphony is triggered. First, the forward collision warning system initiates an aggressive auditory chime and flashes a bright red visual alert on the digital instrument cluster to shatter his distraction. Simultaneously, the system executes a critical preparatory step known as brake pre-fill. The electronic stability control pump quietly forces hydraulic fluid into the brake lines, pushing the brake pads to rest mere millimeters away from the spinning steel rotors. This microscopic adjustment eliminates the mechanical slack in the braking system, shaving precious milliseconds off the mechanical deployment time. If David looks up and slams the brake pedal, the system will apply brake assist, recognizing his panic stop and automatically maximizing the hydraulic pressure far beyond what his foot could achieve, utilizing electronic brake force distribution to prevent the wheels from locking. But what if David does not react in time? If the algorithmic threshold for an unavoidable collision is breached, the automatic emergency braking system overrides human input entirely. It commands maximum hydraulic pressure to the calipers. The anti-lock braking system pulses the brakes dozens of times per second to maintain tire adhesion with the Texas asphalt. The seatbelt pretensioners fire, pulling David back securely into his seat to position him perfectly for potential airbag deployment. The kinetic energy of the heavy vehicle is violently converted into thermal energy at the brake rotors, hauling the car down from highway speeds to a dead stop. This entire sequence of detection, calculation, and mechanical intervention occurs in a time frame measured in fractions of a single second. When we analyze historical trends and case studies provided by organizations like the Insurance Institute for Highway Safety, the potential outcomes of widespread automatic emergency braking adoption become staggeringly clear. Statistical data suggests that vehicles equipped with these active systems show a dramatic reduction in the frequency of rear-end striking collisions, often mitigating the crash entirely or significantly reducing the impact speed, which directly correlates to a massive reduction in severe whiplash injuries and costly property damage liability claims. However, it is fundamentally crucial to understand that these systems operate under strict physical laws and situational constraints. They are tools of mitigation, not absolute shields of invulnerability. A sudden blinding glare from a setting sun can temporarily blind the optical cameras. A heavy layer of wet snow accumulating over the front bumper can completely block the radar waves from emitting, rendering the system functionally blind and instantly transferring all safety responsibilities back to the human driver. As we continue to monitor the potential outcomes of these technologies on our modern highways, it becomes evident that mastering the space directly in front of the vehicle is only the first dimension of the safety equation. The forward-facing sensors are constantly scanning the horizon, calculating closing speeds, and preparing the hydraulic brakes for sudden deceleration. But highway driving is rarely a straightforward, linear experience. Vehicles are constantly shifting, merging, and drifting across multiple lanes of travel at high speeds. What happens when the imminent danger is not a stopped car directly in your path, but a heavy commercial truck slowly wandering into your blind spot from the side? Or when highway fatigue sets in and your own vehicle begins to gently drift over the solid yellow line toward oncoming traffic? The forward sensors are completely useless in these lateral scenarios, requiring an entirely different architecture of localized sensor networks and steering column interventions that operate on a totally different set of algorithmic rules. This transition from longitudinal safety, which manages the space directly in front of and behind your vehicle, to lateral safety, which manages your side-to-side movements, represents one of the most significant engineering leaps of the last decade. To understand how your vehicle prevents you from sideswiping a tractor-trailer or drifting off a dark rural highway, we must examine the localized sensor networks embedded within the rear quarter panels and side mirrors. Unlike the powerful 77 GHz long-range radar mounted in your front grille that can pierce through weather to see hundreds of feet ahead, the lateral safety architecture relies heavily on a specialized array of 24 GHz short-range radar modules and high-frequency ultrasonic sensors. These devices are completely invisible from the outside, hidden behind the painted plastic of your rear bumper, but they are constantly projecting a wide, fan-shaped electromagnetic net around the rear corners of your car. These short-range radars are specifically calibrated to monitor the adjacent lanes. They are not simply looking for the presence of an object. They are performing complex, continuous trigonometric calculations to determine the exact trajectory and closing speed of vehicles approaching from your rear blind spots. Consider the daily reality of a driver named Sarah, navigating the heavily congested, 5-lane expanse of Interstate 90 outside of Chicago in the year 2026. It is late afternoon, traffic is dense, and the ambient noise is high. Sarah needs to merge left to catch her upcoming exit. She checks her rearview mirror, glances at her side mirror, activates her turn signal, and begins to turn the steering wheel. However, obscured entirely by the thick structural pillar between her side and rear windows, a blind spot that has actually grown larger in modern vehicles due to stricter roof crush safety mandates, is a low-profile sports car accelerating rapidly to pass her. In a vehicle lacking active lateral safety systems, this exact scenario plays out thousands of times a day across the United States, frequently resulting in high-speed sideswipe collisions that send vehicles spinning out of control across multiple lanes of traffic. But Sarah is driving a modern machine equipped with active blind spot intervention. Milliseconds after she activates her turn signal, the 24 GHz radar in her left rear bumper detects the rapidly closing mass of the sports car. The system recognizes that a collision is mathematically imminent if her current steering trajectory continues. First, the visual indicator embedded in her left side mirror illuminates with a piercing brightness, accompanied by an urgent, high-decibel auditory warning echoing through the cabin speakers. But human reaction time is inherently flawed, and Sarah is already committed to the lane change, her hands actively turning the wheel. This is the exact moment where passive monitoring transforms into active physical intervention. Because Sarah is not correcting her course, the vehicle's central electronic control unit instantaneously overrides her manual input. It does this through a magnificent piece of engineering known as the electronic power steering system. Historically, steering columns were purely mechanical, assisted by hydraulic fluid pumps driven by the engine. But to allow a computer to steer a car, engineers had to sever that pure mechanical link and introduce an electric motor mounted directly to the steering rack. When the blind spot algorithm triggers an emergency intervention, it sends a digital command to this electric motor. The motor instantly applies precisely calculated rotational torque to the steering column, gently but firmly physically fighting Sarah's hands, countersteering the vehicle back into the center of her original lane. Simultaneously, the system may apply asymmetric braking, lightly pulsing the brakes on the right side of the vehicle only, using the resulting drag to pivot the car away from the danger on the left. The sports car flies past unharmed. Sarah remains safely in her lane. This mechanical takeover is not limited solely to avoiding other vehicles in your blind spot. It is the exact same foundational hardware that enables lane keeping assist and road departure mitigation. However, while blind spot systems rely on radar to detect solid metallic objects, lane keeping systems rely almost entirely on the forward-facing stereoscopic cameras to detect something far more fragile: painted lines on the asphalt. As you drive down the highway, the optical camera behind your rearview mirror is capturing video at 60 frames per second. An incredibly sophisticated computer vision algorithm processes every single frame in real time, executing a process known as edge detection. The software scans the visual data looking for high-contrast boundaries, specifically the stark difference between dark gray asphalt and white or yellow reflective paint. Once the algorithm successfully maps the lane markings on both the left and right sides of your vehicle, it creates a virtual corridor in its digital mind. It then calculates the exact dead center of that corridor. As you drive, if you begin to drift due to fatigue, distraction, or simply reaching for a cup of coffee, the system recognizes that your vehicle's trajectory is deviating from that mathematically perfect center line. If your tires approach the painted boundary without an active turn signal indicating an intentional lane change, the electronic power steering motor engages once again, applying just enough torque to nudge the steering wheel and guide the heavy machine back toward the center. When we analyze historical trends regarding highway fatalities, the integration of these lateral intervention systems represents a monumental shift in potential outcomes. Single-vehicle runoff road crashes, where a drowsy or distracted driver simply drifts off the pavement and strikes a tree, an embankment, or a concrete barrier, have historically accounted for a massive and tragic percentage of severe automotive wrecks in the United States. By actively intervening to keep the vehicle within its designated lane of travel, modern safety systems are fundamentally altering the statistical probability of these devastating accidents occurring. The machine is acting as a tireless, vigilant co-pilot that never blinks, never gets distracted by a mobile device, and never falls asleep at the wheel. Yet, we must acknowledge the strict parameters and absolute physical limitations governing these remarkable interventions. The engineering mandate requires that the human driver must always be able to physically overpower the computer. The electric motor on the steering rack is programmed with a strict torque limit. If you grip the wheel firmly and force a lane change, the system will yield to your manual override, assuming you see a danger that the cameras and radar have missed. Furthermore, the entire foundation of lane keeping assist is completely dependent on the optical clarity of the environment. The camera must be able to clearly see and mathematically define the painted lines to create its virtual corridor. This introduces a critical and highly documented vulnerability in the modern transportation ecosystem. What exactly happens when the environment stops cooperating with the algorithms? Imagine driving through a heavy, sudden blizzard where a layer of fresh white snow completely obscures the painted lines on the road. Or consider the chaotic, confusing environment of a highway construction zone, where the old white lines have been poorly scraped away, temporary orange lines intersect them at odd angles, and concrete barriers heavily restrict the physical space. In these highly complex, low-visibility scenarios, the camera's edge detection algorithm experiences a catastrophic failure of logic. It can no longer confidently map the lane. Suddenly, without warning, the green steering wheel icon on your dashboard turns gray. The invisible rails guiding your car vanish. The system silently disengages, instantly transferring the immense physical responsibility of steering a 2-ton kinetic missile entirely back to you, often precisely at the moment when the driving conditions are at their absolute worst. How the human brain reacts to this sudden, jarring transition of control, and why it frequently results in disastrous panic corrections, is a terrifying psychological phenomenon that we must explore next. When the invisible rails vanish and the system silently disengages, we crash headfirst into one of the most thoroughly documented and perilous paradoxes in modern human factors engineering. In the cognitive science and human-machine interface communities, this is known as the out-of-the-loop performance problem, or more simply, the handoff problem. To truly grasp why these split-second transitions of control often result in severe accidents, we have to look past the microchips and radar sensors and turn our analytical focus toward the most complex, yet historically flawed processor in the vehicle, the human brain. For decades, historical trends in aviation have shown that as automated flight systems became increasingly reliable, human pilots systematically lost their manual edge. Today, in 2026, we are witnessing this exact same phenomenon play out on a massive scale across the American highway system. We have engineered vehicles that handle 99% of the driving task flawlessly, which inadvertently conditions the human operator to be entirely unprepared for the critical 1% when the system abruptly fails. The fundamental flaw lies in our neurological wiring. The human brain is evolutionarily optimized for active engagement and dynamic problem-solving, but it is notoriously terrible at sustained, passive monitoring. When you are actively steering a car, feeling the resistance of the road through the steering column, and manually managing the throttle, your sympathetic nervous system is engaged. Your eyes are constantly scanning. Your peripheral vision is actively processing spatial data. But when you activate adaptive cruise control and lane keeping assist, you transition from an active operator to a passive passenger sitting in the driver's seat. Within roughly 15 to 20 minutes of this transition, a documented physiological shift occurs called the vigilance decrement. Your blink rate slows down. Your gaze becomes fixed and central rather than actively scanning the periphery. Your brain, prioritizing energy conservation, essentially powers down its active threat detection centers because the machine has successfully proven it can handle the workload. You enter a state of automation complacency, a dangerous psychological comfort zone where you subconsciously trust the vehicle to save you from environments it was never actually programmed to navigate. Imagine the very real scenario of a driver named Mark, The year is 2026, and Mark is driving a highly equipped, modern sport utility vehicle north on a winding high-speed stretch of Route 1 in California. It is late evening, the sky is overcast, and Mark is relying heavily on his vehicle's Level 2 advanced driver assistance systems to navigate the gentle curves along the coastline. For the last 40 miles, the system has performed magnificently. The cameras have tracked the bright white lane markings, and the radar has maintained a safe following distance. Mark's hands are resting lightly on the bottom of the steering wheel, technically compliant with the vehicle's torque sensor requirements, but his cognitive focus is completely detached from the physical reality of the road. He is listening to a complex financial podcast, his mind visualizing market trends rather than calculating the parabolic trajectory of the upcoming coastal curve. He is physically present, but cognitively he is miles away. Suddenly, the environment drastically shifts. The well-maintained asphalt transitions into an active construction zone. The bright white lines abruptly end, replaced by faded, temporary lane shifts that intersect with the old markings. Simultaneously, the coastal fog rolls in thicker, severely degrading the optical contrast the stereoscopic cameras require to perform their edge detection algorithms. The system computer attempts to process this conflicting, degraded data. Within milliseconds, it reaches a threshold of mathematical uncertainty. It simply cannot calculate a safe path. Following its rigidly programmed safety protocol, the system immediately disengages to prevent steering the vehicle into an incorrect lane. A loud, sharp audible chime pierces the cabin, and a sudden red visual warning flashes across the dashboard. This is the exact moment the handoff problem becomes critically dangerous. When a driver is fully engaged, the average reaction time to an unexpected highway event is approximately 1.5 seconds. But multiple case studies and simulator trials have demonstrated that when a driver is completely out of the loop and startled by an abrupt system disengagement, that reaction time can easily double or even triple. Mark's brain is jolted back to reality by the chime. This triggers an immediate, involuntary physiological reaction known as the startle response. His adrenal glands instantly flood his bloodstream with cortisol and adrenaline. Before his visual cortex has even fully processed the confusing construction zone markings, his fine motor skills are severely compromised by the sudden chemical surge. When he finally registers that the car is drifting toward heavy concrete barricades because the steering assist has vanished, sheer panic sets in. He grips the wheel, and instead of applying a smooth, calculated corrective input, his compromised motor control results in a massive, jerky overcorrection. This panicked oversteer violently shifts the 2-ton vehicle's center of gravity. The heavy sport utility vehicle pitches sharply to the left. At 65 miles per hour, this sudden lateral weight transfer completely overwhelms the available mechanical grip of the front tires. The vehicle begins to yaw violently, entering a high-speed skid across the wet asphalt. In the span of 4 seconds, Mark has gone from a relaxed, passive monitor to fighting for his life in a catastrophic loss of control event, entirely initiated by the sudden transfer of responsibility from a failing algorithmic safety net to an unprepared human mind. The advanced safety features did not directly cause the crash, but the psychological complacency they induced created the perfect environment where a minor environmental anomaly cascaded into a major kinetic disaster. To combat this exact phenomenon, automotive engineers in 2026 have increasingly deployed internal driver monitoring systems. These utilize sophisticated infrared cameras mounted on the steering column or rearview mirror to actively track the driver's eye movements, blink rate, and head position. If the system detects that your eyes have wandered from the road for too long, it escalates auditory warnings, eventually disabling the cruise control entirely to force manual engagement. However, historical trends reveal a constant cat-and-mouse game between safety engineering and human behavior. Drivers quickly learn the minimum viable compliance required to silence the alarms. They learn to keep their heads pointed forward, while their cognitive attention remains completely absorbed by a hands-free phone conversation or a dashboard infotainment screen. The infrared camera sees open eyes looking forward, satisfying the algorithmic requirement for visual attention. Yet the mind behind those eyes is entirely unequipped to handle a sudden emergency handoff. This creates a terrifying false positive in the vehicle's safety matrix, proving that visual attention does not guarantee cognitive awareness. Drivers are trusting these systems implicitly, treating them as infallible robotic chauffeurs rather than the fragile condition-dependent assist modules they actually are. Manufacturers continually issue warnings and mandate that drivers must remain attentive, But human psychology is incredibly resistant to corporate disclaimers in the face of perceived convenience. If a machine works perfectly 999 times, the human brain is practically hardwired to assume it will work perfectly on the 1000th attempt. This deeply ingrained cognitive bias is arguably the single greatest hurdle the automotive industry faces today. We are trying to solve a fundamentally human psychological problem with increasingly complex lines of code, and the results on the asphalt are proving to be devastatingly unpredictable. So, if the high-definition cameras can be blinded by coastal fog, if the millimeter-wave radar can be jammed by snow, and if the human brain is psychologically incapable of snapping back to attention fast enough to manage the sudden handoff, what happens when the algorithms completely fail and the crash becomes unavoidable? When active safety systems surrender to the unforgiving laws of physics, the absolute last line of defense is the physical architecture of the vehicle itself. The moment the metal begins to crush, an entirely different, intensely violent mechanical ballet begins, and understanding how modern vehicles are meticulously engineered to systematically destroy themselves in order to keep you alive is a terrifying masterpiece of structural physics that we must dissect right now. When a modern vehicle strikes a solid, immovable object at highway speeds, a terrifying and magnificent sequence of mechanical events unfolds in a time frame that is significantly faster than the blink of a human eye. To comprehend this, we have to look closely at historical trends in automotive manufacturing. For decades, the prevailing logic among American consumers was that a heavier, more rigid vehicle equated to a safer vehicle. If you look at the massive steel land yachts cruising the highways in the 1970s, they were built like bank vaults. The public assumption was that in the event of a crash, the car should survive without a dent. But historical crash data and biomechanical research revealed a fatal flaw in this logic. When a perfectly rigid structure hits a concrete wall at 60 miles per hour, the vehicle stops instantaneously. Because the vehicle does not absorb any of the kinetic energy through structural deformation, 100% of that violent bone-shattering force is transferred directly into the passenger cabin, and consequently, into the fragile human body strapped inside. The car might survive the wreck beautifully, but the internal organs of the occupants would suffer catastrophic, unsalvageable deceleration trauma. Modern automotive engineers flipped this paradigm completely upside down. They realized that to save the human, they had to intentionally destroy the car. This led to the creation and perfection of the crumple zone, arguably the most important passive safety feature ever integrated into a chassis. Imagine a driver named Michael, commuting home from his office in Denver, Colorado, in the year 2026. He is driving a late-model midsize sedan. As he crosses a busy intersection, a heavy pickup truck running a red light completely ignores all active safety warnings and crosses directly into his path. A severe frontal offset collision is no longer a mathematical probability. It is an absolute physical certainty. The moment Michael's front bumper makes contact with the side of the truck, the first 10 milliseconds of the crash begin. In a 2026 vehicle, the front bumper is not designed to repel the impact. It is a sacrificial lamb made of thermoplastic and lightweight aluminum, designed to immediately shatter and initiate the energy absorption process. Behind that bumper lie the front frame rails. These are not solid blocks of steel. They are highly engineered, hydroformed metal structures specifically stamped with intentionally weakened areas called crush dimples or crush initiators. Think of them like the pre-scored lines on a cardboard box. When the massive kinetic force of the impact hits these rails, they do not simply bend randomly. They are mathematically programmed to fold onto themselves in a highly predictable, progressive manner. As Michael's car continues to crush inward during milliseconds 20 through 40, the folding metal is actively doing the work of deceleration. Every single time a piece of steel bends and tears, it is converting the kinetic energy of the crash into heat and acoustic energy. This deliberate structural failure acts as a massive mechanical sponge, violently absorbing the destructive forces so that Michael's body does not have to. The engine block, which is a massive, solid piece of aluminum and iron that physically cannot crush, is specifically mounted on breakaway engine mounts. Instead of being pushed directly backward into the passenger cabin and crushing Michael's legs, the mounts snap under the immense pressure, forcing the entire engine block to drop safely downward and slide underneath the floor pan of the vehicle. By millisecond 50, the entire front third of Michael's sedan has essentially been destroyed. It looks like a catastrophic amount of damage, and to an untrained observer, it looks like a horrific, fatal wreck. But this extensive damage is exactly what the engineers intended. However, this controlled destruction must stop before it reaches the occupants. This brings us to the second and equally critical component of modern structural physics, the safety cell. While the front and rear of the vehicle are designed to be as soft and yielding as possible, the passenger cabin itself is constructed to be an impenetrable fortress. To achieve this, manufacturers utilize a completely different class of materials, predominantly ultra-high-strength steel and boron steel. Boron steel is so incredibly hard that it cannot be stamped or cut using traditional manufacturing methods. It must be heated to extreme temperatures and formed while red-hot before being rapidly cooled, a process known as hot stamping. The pillars framing the windshield, the reinforced beams inside the doors, and the primary structural rings wrapping around the roof and floor are entirely constructed from these advanced alloys. When the kinetic energy from the crash reaches the firewall, which is the physical barrier separating the engine compartment from the interior cabin, the structural logic of the car instantly changes from yielding to absolute resistance. The remaining crash energy that was not absorbed by the crumple zones hits the safety cell and is actively redirected. The boron steel structural rings act like a hardened cage, channeling the destructive force over the roof, down through the door sills and underneath the floor pan, effectively routing the energy entirely around Michael rather than through him. Consider the rigorous testing protocols that forced this specific evolution. For years, historical trends showed that vehicles performed adequately in full frontal crash tests, where the entire width of the car absorbed the impact. But engineers noticed a disturbing anomaly in real-world case studies. Drivers were still suffering severe injuries in offset collisions, where only a small fraction of the front bumper struck an object, like a utility pole or the edge of an oncoming vehicle. Because the impact missed the primary frame rails entirely, the vehicle's crumple zones were bypassed. The utility pole would slice through the soft headlight assembly and strike the rigid safety cell directly, tearing through the driver's footwell and collapsing the steering column. To combat this, independent testing agencies introduced the small overlap front crash test, arguably the most brutal and demanding structural assessment in the automotive industry. This forced manufacturers to radically redesign the entire foundational architecture of their vehicles. If you look closely at the underlying chassis of a 2026 model year vehicle, you will notice highly complex, lateral deflector plates and reinforced structural horns protruding outward toward the front wheels. These structures are specifically engineered to catch an offset impact and force the vehicle to physically slide sideways, glancing off the object rather than absorbing the full blow directly into the passenger compartment. This intricate geometry ensures that even if only 20% of the front bumper is engaged in the collision, the kinetic energy is still captured and successfully routed into the main energy-absorbing load paths. Furthermore, the materials science behind this is staggering. The transition from the soft, low-carbon steel of the crumple zone to the ultra-high-strength boron steel of the safety cell is not an abrupt line. Automotive metallurgists utilize a technique called tailor-welded blanks. This process involves laser welding different grades and thicknesses of steel together into a single, continuous sheet before it is ever stamped into a car part. This allows engineers to micromanage the exact flow of crash energy. The metal starts thick and soft at the front to crush easily, gradually becoming thinner but exponentially harder as it nears the passenger compartment, creating a seamless, mathematically perfect deceleration ramp for the kinetic energy to travel down. In our scenario with Michael at millisecond 80, the vehicles finally come to a complete physical rest. The front end of his sedan is an unrecognizable mass of twisted metal and shattered plastic. The radiator is destroyed, the front axle is snapped, and the hood is folded perfectly in half. Yet, remarkably, the doors of the safety cell remain intact and perfectly aligned. Michael can actually reach out and open his door using the handle because the structural integrity of the cabin has not been compromised by even a fraction of an inch. The potential outcomes of this specific engineering philosophy are profoundly evident in modern crash statistics, where occupants are routinely surviving high-speed collisions that would have been guaranteed fatalities just 2 decades ago. The car has performed its ultimate duty. It has sacrificed its own structural life to preserve the biological life inside it. But here is the terrifying reality that we must confront next. While the boron steel safety cell successfully stopped the intrusion of twisted metal, and the crumple zones dramatically slowed down the vehicle, the physical laws of inertia dictate that Michael's body is still moving forward at the exact original speed of the vehicle prior to the crash. The car has stopped, but the human organs inside the chest cavity have not. If left unchecked, this internal kinetic energy will cause the human body to violently strike the steering wheel, the dashboard, or the windshield, resulting in catastrophic internal injuries despite the cabin remaining completely intact. To arrest this secondary human collision, the vehicle must execute an entirely different class of explosive, pyrotechnic interventions that operate in microsecond timeframes, a violent and microscopic ballet of chemical reactions, and woven nylon that will dictate the final outcome of the wreck. To understand this microscopic ballet, we must first confront the terrifying physical reality of the second collision. When a vehicle traveling at 65 miles per hour strikes a completely stationary object, the external structure of the car crushes and comes to a halt in roughly 1/10 of a second. However, the human beings sitting inside the cabin are still traveling at exactly 65 miles per hour. Their skeletal structures, their internal organs, and their brains are all carrying an immense amount of kinetic energy. If the vehicle simply stopped and offered no internal kinetic management, the human body would launch forward, striking the steering column, the dashboard, or the laminated glass of the windshield. This internal impact is historically what causes the most severe, life-altering trauma. To prevent this, automotive engineers in 2026 rely on a highly synchronized network of sensors, explosives, and advanced textiles that execute their life-saving protocols faster than human nerve impulses can travel. Imagine a driver named Jessica, commuting on a frozen highway in upstate New York. A patch of black ice causes the vehicle ahead of her to spin out, resulting in an unavoidable high-impact frontal collision. At exactly 10 milliseconds after the initial bumper impact, solid-state accelerometers bolted deeply into the rigid chassis of Jessica's vehicle detect a massive instantaneous spike in negative gravitational forces. These sensors are essentially microscopic tuning forks etched into silicon chips. When the deceleration threshold exceeds normal hard braking parameters, the sensors send a high-voltage electrical signal to the restraint control module, which serves as the central brain for the entire supplemental restraint system. By millisecond 15, the restraint control module has analyzed the severity of the crash, the weight of the occupants sitting in the seats, and the exact position of the seats on their tracks. It then sends an electrical firing current to the very first line of defense, which is not the airbag, but rather the pyrotechnic seatbelt pretensioner. For decades, the public viewed the seatbelt as a static, passive strip of woven nylon. In a modern vehicle, the seatbelt is a highly active, explosive device. Hidden deep inside the pillar of Jessica's car, right next to the seatbelt spool, sits a tiny cylinder packed with a combustible chemical propellant, very similar to the fast-burning compounds used in solid rocket boosters. When the electrical signal arrives, it ignites this propellant. The resulting micro-explosion generates rapidly expanding gas that violently drives a piston down a tube. This piston is mechanically linked to the seatbelt retractor spool via a rack and pinion gear. In a fraction of a millisecond, the spool is forcefully spun backward, instantly reeling in up to 6 inches of slack from the seatbelt webbing. Before Jessica's body has even begun to physically move forward in response to the crash, the seatbelt violently tightens, pinning her shoulders and pelvis firmly against the seat back. This ensures she is in the absolute perfect geometric position for the next phase of the restraint sequence. However, there is a severe physical limit to this mechanical grip. If the seatbelt simply locked completely solid after retracting, the immense forward momentum of Jessica's body against the 2-inch wide nylon strap would concentrate thousands of pounds of force directly onto her collarbone and rib cage. Historical trends in automotive medicine showed that while early seatbelts saved lives, they frequently caused severe localized fractures. To solve this, engineers integrated a brilliant mechanical fuse known as a load limiter. The spool that holds the seatbelt is attached to the frame via a precisely machined, twisted steel torsion bar. As Jessica's body weight pushes forward against the locked belt, the force reaches a critical threshold. At that exact moment, the steel torsion bar is designed to physically twist and intentionally deform, slowly releasing a few inches of seatbelt webbing. This controlled yielding acts like a shock absorber for the human torso, allowing Jessica's upper body to ride the crash down and decelerate at a survivable rate, rather than suffering a massive blunt force trauma from the belt itself. Simultaneously, at millisecond 20, as the seatbelt is actively managing her torso, the restraint control module initiates the deployment of the frontal airbags. There is a massive public misconception regarding how airbags operate. They are not filled with compressed air from a tank. They are essentially solid fuel engines completely engineered to burn out in roughly 30 milliseconds. Inside the hub of the steering wheel sits an inflator module packed with precisely measured pellets of guanidine nitrate, a highly stable but incredibly energetic chemical compound. The electrical signal ignites a heating element that instantly vaporizes the chemical pellets. The solid guanidine nitrate undergoes a rapid, violent phase change, instantly converting into a massive volume of harmless nitrogen gas. This gas rapidly expands, tearing through the purposely weakened seams of the plastic steering wheel cover at a speed exceeding 200 miles per hour. By millisecond 30, the nylon fabric bag is fully inflated directly in front of Jessica's face. But here is the most critical engineering detail of the entire sequence. An airbag is not a pillow. If Jessica struck a fully inflated, sealed airbag, it would be identical to hitting a concrete wall, causing severe neck and spinal injuries. The airbag is actually a highly sophisticated energy dissipation mechanism. Strategically cut into the back of the airbag fabric are specialized vent holes. The exact moment Jessica's face makes contact with the front of the airbag, the nitrogen gas is violently forced out of those rear vents. She is not bouncing off the airbag. She is actively crushing it, forcing the gas out to safely decelerate the fragile bones of her face and skull. Modern 2026 vehicles take this a step further with dual-stage inflators. The restraint control module uses weight sensors in the seat to determine the exact mass of the occupant. If Jessica were a lightweight driver, the system would only ignite 70% of the chemical propellant, creating a softer, more forgiving airbag deployment. If the occupant were a heavier individual, the system would ignite the full charge to prevent them from pushing completely through the airbag and striking the steering column. Furthermore, the restraint environment has evolved into a three-dimensional cocoon. While the frontal airbag catches the face, side curtain airbags deploy downward from the roof rail to cover the side windows, preventing Jessica's head from striking the shattered glass or the intruding hood of the other vehicle. Torso airbags explode outward from the sides of the seat to protect her ribs and vital organs from lateral crushing forces. Even the lower extremities are protected, with knee airbags deploying from under the dashboard to keep her femurs from shattering against the rigid plastic trim. Within 50 milliseconds, exactly half the time it takes for a human to blink, the vehicle has executed dozens of localized explosions, perfectly choreographing the deceleration of multiple body parts across 3 different axes of movement. This extraordinary timeline of mechanical and chemical intervention represents the absolute pinnacle of passenger preservation. The potential outcomes of surviving a massive kinetic event are vastly improved compared to historical trends because the vehicle actively manages the physical limitations of the human body. However, once the dust settles, the glass stops shattering, and the chemical smoke clears from the cabin, the true aftermath of the wreck begins. The vehicle has sacrificed its structure and deployed its ultimate countermeasures to keep the occupants alive, but sitting inside a heavily damaged, completely immobilized vehicle on a busy, frozen highway presents an entirely new matrix of life-threatening dangers. How modern vehicles transition from pre-crash avoidance to explosive in-crash mitigation, and finally into an automated, highly intelligent post-crash survival mode that instantly alerts the outside world, is a critical evolution in emergency response that we are going to completely unpack next. The violent kinetic exchange is over. The airbags have deflated, leaving a haze of talcum powder and inert nitrogen gas suspended in the cabin. The crushing sound of tearing boron steel has been replaced by an eerie, sudden silence. But while the physical collision has ended, the digital response is just initiating. Historically, survival in the aftermath of a severe accident in a remote location relied entirely on the hope that a passing motorist would witness the wreckage and physically drive to an area with cellular service to call for help. Historical trends in emergency medicine dictate a concept known as the golden hour, a critical 60-minute window following severe trauma where rapid medical intervention exponentially increases the potential outcomes for survival. In decades past, victims trapped in rural wrecks routinely bled out or succumbed to exposure simply because the clock ran out before anyone even knew they were in danger. Today, in 2026, the modern vehicle eliminates that deadly communication gap entirely by transforming from a mode of transportation into a highly intelligent, self-reporting emergency beacon. Imagine a driver named Robert, traveling on a desolate, pitch-black stretch of Interstate 80 through Wyoming at 2 in the morning. Black ice causes his truck to leave the elevated roadway and roll down a steep embankment, coming to rest out of sight from the highway above. Robert is unconscious. His smartphone has been violently thrown somewhere in the dark cabin. In 1998, this scenario is a near-certain fatality. In 2026, the vehicle itself takes absolute control of the rescue operation. Within a fraction of a second after the airbags deploy, the restraint control module triggers an irreversible cascade of post-crash safety protocols designed to secure the immediate environment. First, a specialized pyrotechnic fuse located directly on the main 12-volt battery terminal is intentionally blown. This completely severs the connection to the heavy-gauge alternator cable, instantly cutting power to the primary engine electronics to prevent an electrical fire, while deliberately maintaining a secondary power circuit exclusively for the telematics system and the cabin doors. Simultaneously, the central computer sends a digital command to the fuel pump module located inside the gas tank, shutting it down immediately. This critical step stops highly flammable gasoline from pumping out of potentially severed fuel lines onto the scorching hot exhaust manifold. The electronic door locks automatically disengage, ensuring that if first responders arrive, they will not have to waste precious minutes utilizing hydraulic rescue tools to pry open a locked door. Finally, the interior dome lights illuminate to maximum brightness to assist the dazed occupants, and the exterior hazard lights begin flashing at a high-frequency strobe rate to visually alert any distant oncoming traffic. But the true life-saving masterpiece is happening invisibly through the cellular spectrum. Embedded deep within the dashboard is a telematics control unit, essentially an armored, crash-hardened cellular modem with its own dedicated backup battery and a heavy-duty antenna hidden inside the roof structure. The moment the crash algorithms register a deployment event, this unit wakes up and initiates an automatic crash notification sequence. It bypasses commercial cellular networks and connects directly to emergency dispatch systems. It does not just call for help, it transmits a dense, encrypted data packet detailing the precise anatomy of the wreck. Before a human operator ever speaks through the vehicle speakers, the 911 dispatcher sitting hundreds of miles away in a regional call center receives a glowing alert on their monitor. This data packet contains the exact GPS coordinates of Robert's truck, precise to within a few feet. But it goes so much deeper than just location. The vehicle transmits the exact delta V, which is the instantaneous change in velocity experienced during the impact. By looking at this number, trauma surgeons can accurately predict the severity of internal organ damage before the ambulance even leaves the hospital bay. The telemetry data tells the dispatcher exactly which airbags deployed, indicating the direction of the impact. It transmits data from the seatbelt weight sensors, informing emergency services exactly how many passengers were in the vehicle, so they know exactly how many ambulances to dispatch. It even reports whether the vehicle came to rest on its roof or its wheels. Once this data handshake is complete, the telematics unit opens a live, two-way audio channel through the vehicle's infotainment speakers and a high-gain microphone mounted in the headliner. A trained emergency medical dispatcher will attempt to speak with Robert. If Robert is unconscious and cannot reply, the dispatcher does not hang up, because the telemetry data already confirmed the severity of the crash and the exact location. The dispatcher immediately routes police, fire, and emergency medical services to the coordinates. This system single-handedly shrinks the discovery phase of an accident from hours to literally seconds, entirely neutralizing the isolation factor of rural highway driving. Case studies analyzing trauma center admissions in recent years demonstrate the staggering impact of automatic crash notification systems. First responders are arriving on scenes with specialized equipment tailored exactly to the data the car provided. If the telematics indicate a high-speed rollover with a localized impact on the driver's side door, fire departments can load specialized heavy-duty extrication equipment onto the primary response truck, rather than arriving with standard gear and having to call for a secondary rescue unit. Hospital trauma teams are activated and pre-briefed on the anticipated injuries based solely on the mathematical physics transmitted by the crushed vehicle. The synergy between automotive engineering and modern emergency response infrastructure has effectively rewritten the survival metrics of catastrophic collisions. Yet, as we marvel at the intricate choreography of sensor fusion, boron steel cages, and cellular emergency beacons, we must inevitably confront the massive elephant in the room. This incredible matrix of life-saving technology comes with an astonishing, almost incomprehensible financial burden. We have effectively replaced cheap, easily reparable metal bumpers with highly calibrated sensor arrays that cost as much as a used car to replace. When a minor fender bender in a parking lot suddenly destroys a radar module, a stereoscopic camera, and 2 ultrasonic sensors, who actually pays the bill? The financial ecosystem surrounding these advanced driver assistance systems is currently sending shockwaves through the entire auto insurance industry, driving premiums to historic highs and creating a highly volatile market where minor accidents result in complete vehicle total losses. How this economic reality impacts your wallet, and why your insurance company fundamentally distrusts the very safety features they claim to promote, is a deep financial paradox that requires an entirely new level of investigation. To fully grasp this financial paradox, we must completely deconstruct the hidden economy of the modern auto body repair industry. Let us look at a highly common scenario playing out thousands of times a day across the country. Imagine an American driver named Thomas. The year is 2026 and Thomas is navigating a crowded grocery store parking lot in suburban Atlanta driving a late-model, fully equipped crossover utility vehicle. He is distracted for a fraction of a second, his foot slips on the pedal, and he gently taps a concrete light pillar at approximately 4 miles per hour. The impact is barely enough to spill his coffee. He backs up, puts the vehicle in park, and steps out to inspect the damage. He sees a scuffed plastic front bumper cover, a slightly cracked lower grille, and a small indentation. If we look at historical trends from just 20 years ago, this exact scenario was a minor inconvenience. Thomas would take his car to a local independent body shop. The mechanic would order a piece of unpainted plastic, spray it to match the factory color code, snap it onto the mechanical clips, and Thomas would pay perhaps $400 out of pocket. He might not even report it to his insurance company to avoid a premium hike. But in 2026, Thomas is not just looking at a piece of molded plastic. He is looking at the shattered outer shell of a highly calibrated, highly sensitive electronic nervous system. Behind that slightly scuffed bumper cover sits the master millimeter wave radar module responsible for his adaptive cruise control and forward collision warning. To the left and right are ultrasonic parking proximity sensors. Tucked behind the cracked lower grille is the ambient air temperature sensor and the active aerodynamic shutter system. The physical damage to the plastic is entirely negligible, but the fragile aluminum bracket holding the primary radar module has been bent backward by precisely 3 millimeters. That 3 millimeter deviation is about to trigger a financial avalanche. When Thomas takes this vehicle to a certified collision center, the true scope of the modern repair protocol begins. The body shop cannot simply bend the bracket back into place and snap a new piece of plastic over it. The very first step of the repair process involves plugging a proprietary manufacturer-specific diagnostic computer into the vehicle to run a pre-scan. This scan queries every single electronic control unit in the car to see what fault codes were thrown during the 4 mile per hour impact. This diagnostic scan alone often costs a minimum of $150. Then comes the replacement phase. These sensors are not generic aftermarket parts you can buy at a local auto parts store. They are proprietary, mathematically matched components that must be ordered directly from the manufacturer. The primary radar module alone carries a retail price of $1,200. The ultrasonic sensors are $200 each. The wiring harness that connects them, which was pinched against the concrete pillar, must be completely replaced because modern safety data lines cannot be spliced or taped back together without degrading the signal quality. We are instantly at a baseline of almost $2,000 in raw materials before a single technician has even picked up a wrench. But the most staggering cost is found in the final phase of the repair, a highly complex procedure known as ADAS calibration. This is the exact moment where the financial paradox truly materializes. You cannot simply bolt a new radar module onto the front of a vehicle and expect it to work. If that radar is bolted on even 1 single degree off its mathematical center line, the geometric cone of its vision is drastically altered. At highway speeds of 70 miles per hour, a 1 degree misalignment means the car thinks a semi-truck 200 feet ahead is actually in the adjacent lane, or conversely, it perceives a harmless highway overpass support pillar as an imminent collision threat directly in your path. An uncalibrated safety system is essentially a highly dangerous, guided missile of incorrect data. To prevent this, the body shop must perform a static calibration. This requires driving the vehicle into a massive, perfectly level, brightly lit indoor bay. The technician must set up highly specialized, mathematically precise geometric targets on heavy metal stands. These targets must be placed at exact distances from the center line of the chassis, often requiring lasers and plumb bobs to achieve perfect alignment. The vehicle is then connected to a massive computer server that slowly teaches the new radar module exactly where it is positioned in physical space. Following the static calibration, 2 technicians must perform a dynamic calibration, driving the vehicle on an active highway at highly specific speeds, following specific traffic patterns to allow the stereoscopic cameras to recognize lane markings again. This entire calibration process requires hours of highly specialized labor, utilizing equipment that costs the body shop tens of thousands of dollars to purchase and update. That overhead cost is passed directly to the consumer, adding upwards of $600 to $1,000 to the final bill. Thomas receives an estimate for a 4-mile-per-hour parking lot bump that totals over $4,500. This is the exact reason why insurance actuaries are panicking. The foundational mathematics of the auto insurance industry rely on two primary metrics, which are frequency and severity. Historical trends clearly show that advanced driver assistance systems are successfully driving down the frequency of crashes. Cars are simply hitting each other less often. However, the severity metric, which represents the average cost to repair the vehicle when a crash does occur, has skyrocketed to unprecedented, historic highs. The property damage severity curve has completely consumed the financial savings generated by the drop in bodily injury claims. This introduces the terrifying phenomenon of the modern total loss. Because these specific repair costs are so astronomically high, vehicles are being condemned to the scrapyard at alarming rates. Imagine a 5-year-old vehicle with a perfectly healthy engine, a flawless transmission, and zero rust. It suffers a moderate rear-end collision. The cost to replace the rear radar array, the blind spot monitors, the backup camera, the crushed exhaust, and to calibrate the entire network exceeds 70% of the total cash value of the vehicle. The insurance company runs the algorithms and determines it is cheaper to simply write a check for the entire value of the car, rather than attempt to fix the electronic nervous system. A perfectly drivable, mechanically sound machine is destroyed purely because its safety features are too expensive to reboot. The insurance companies are fundamentally trapped in a vicious cycle. They heavily lobby for and mandate these advanced safety features because case studies prove they save human lives and reduce catastrophic medical payouts. Yet, they are forced to drastically raise your monthly insurance premiums to build a massive cash reserve to cover the exorbitant cost of fixing the very sensors that prevented the fatality in the first place. You are essentially prepaying for the inevitable hyper-expensive technological repair in the form of astronomically high monthly rates. Faced with a $4,500 estimate and a massive out-of-pocket deductible, Thomas sits in his driveway and makes a financially pragmatic, yet incredibly dangerous decision. He realizes the engine starts. The wheels turn perfectly. The brakes function. He decides he does not want to pay to fix the radar. He ignores the glowing yellow warning lights permanently illuminated on his digital dashboard. He places a piece of black electrical tape over the cracked plastic sensor housing and drives away. He has actively chosen to operate a highly complex, sensor-dependent vehicle with a completely lobotomized artificial intelligence system. What are the potential outcomes when hundreds of thousands of drivers on the interstate right now are operating vehicles with silently failing, uncalibrated, and intentionally ignored safety nets? We are about to uncover the deeply terrifying reality of deferred maintenance in the digital age, and how the used car market has become a minefield of invisible, lethal liabilities. Let us transition directly into the unseen consequences of Thomas and his electrical tape. For decades, the concept of deferred maintenance in the automotive world was a highly visible mechanical reality. You could visually inspect a used vehicle and easily identify the warning signs of neglect. You could see the metal wire showing through a set of severely bald tires. You could physically hear the high-pitched squeal of metal grinding on metal when brake pads were worn down to their backing plates. You could check the dipstick and smell the burnt, neglected oil. These physical indicators provided a natural, mechanical warning system for the secondary market. But in the year 2026, we have crossed a terrifying threshold into an era of digital deferred maintenance, where the most lethal defects in a vehicle are completely invisible to the human eye, entirely silent, and purposely hidden behind glowing touchscreens and polished sheet metal. Consider the extremely common scenario of a young professional named Amanda. She has recently graduated from university and is navigating the hyperinflated used car market to purchase a reliable commuter vehicle. She finds a beautifully detailed 5-year-old compact sport utility vehicle listed by a private seller on a popular digital marketplace. She walks around the vehicle in a suburban driveway. The paint is flawless. The engine idles smoothly. The interior smells like new leather. She turns the key, and the digital dashboard cycles through its startup animation. There are no check engine lights illuminated. She takes it for a test drive around the neighborhood. The transmission shifts perfectly, and she confidently hands over her life savings to the seller. What Amanda cannot see, and what the private seller intentionally neglected to disclose, is the vehicle's hidden digital history. 2 years prior, that pristine sport utility vehicle was involved in a moderate front-end collision. The previous owner, facing the exact same exorbitant repair estimate that we discussed earlier, opted for an incredibly dangerous off-the-books repair strategy. They took the vehicle to an uncertified discount body shop that specialized in cosmetic fixes rather than structural and electronic restoration. This discount shop replaced the shattered front bumper with a cheap, aftermarket plastic mold that lacked the precise radar-transparent properties of the original manufacturer equipment. More critically, when they bolted the primary millimeter-wave radar module back onto the bent frame bracket, they lacked the $50,000 static calibration equipment required to realign the sensor network. They simply plugged the wiring harness back in, used a pirated software tool to manually clear the fault codes from the internal computer, and pushed the car out the door. Amanda is now operating a kinetic weapon masked as a safe commuter car. The radar module sitting behind her aftermarket bumper is physically skewed precisely 3 degrees to the right. On a microscopic digital level, this means the geometric cone of radar waves her car is actively projecting down the highway is not looking at the lane directly in front of her. It is looking squarely at the concrete median barrier. Furthermore, the previous owner had the cracked windshield replaced by a discount glass company that used generic, non-original equipment glass. This glass possesses microscopic waves and distortions that the original factory glass did not. The high-definition stereoscopic cameras mounted behind her rearview mirror are now essentially wearing the wrong prescription glasses. Their edge detection algorithms and depth perception mathematics are severely corrupted by the distorted light refracting through the cheap windshield. This invisible alignment disaster culminates in a terrifying sequence of events on a rainy interstate exchange. Amanda is traveling at 70 miles per hour in heavy traffic. The vehicle directly in front of her suffers a catastrophic tire blowout and slams on its brakes. Amanda is momentarily distracted by her navigation system. This is the exact microsecond where the advanced driver assistance systems are programmed to save her life. Her vehicle should detect the massive deceleration ahead, pre-fill the brake lines, alert her with auditory chimes, and initiate automatic emergency braking. Instead, an absolute algorithmic failure occurs. The misaligned radar module, staring off into the concrete median, reports to the central computer that the path ahead is completely clear. Simultaneously, the stereoscopic cameras, struggling to process depth through the distorted aftermarket windshield, fail to mathematically confirm the rapidly expanding mass of the braking vehicle ahead. The sensor fusion matrix requires both systems to agree before initiating a panic stop. Because the corrupted data streams contradict reality, the system simply does nothing. There is no auditory warning. There is no pre-tensioning of the seatbelt. There is no automatic braking. Amanda looks up a fraction of a second too late, completely unprotected by the digital safety net she explicitly paid for when she bought the car. The resulting collision is devastating, and the subsequent investigation reveals the darkest secret of the modern used car market. There is currently no national, centralized database that mandates or tracks advanced driver assistance system calibrations. When you purchase a vehicle history report from a major data broker, it might show a minor accident, but it will never tell you if the highly sensitive electronic sensors were mathematically recentered to factory specifications following the repair. The market is absolutely flooded with millions of vehicles that look structurally perfect, but are electronically lobotomized. Drivers are purchasing these vehicles under the strict assumption that they are protected by automatic emergency braking, lane keeping assist, and blind spot monitoring, completely unaware that these systems have been silently rendered useless by improper maintenance and cheap, unauthorized cosmetic repairs. This crisis is further exacerbated by the ongoing battle over the right to repair. Independent, local mechanics are being systematically priced out of the safety ecosystem. When a local mechanic replaces a simple steering angle sensor or a suspension component, they must now perform a dynamic calibration of the entire vehicle to ensure the electronic stability control understands the new mechanical geometry. But automobile manufacturers are increasingly locking down their internal software behind massive digital firewalls, requiring expensive, proprietary subscriptions just to access the calibration menus. Many independent shops simply cannot afford these annual digital tolls, forcing them to either turn away customers, send the vehicles to expensive dealerships, or worse, skip the vital calibration steps entirely and hope the customer never encounters an emergency scenario where the millimeter precision of the sensor network is tested. We have built a transportation infrastructure highly dependent on artificial intelligence, yet we have failed completely to build the regulatory framework required to ensure that intelligence remains sharp, focused, and accurate as the vehicle ages. We are trusting our lives to mathematical algorithms that are actively degrading with every uncalibrated windshield replacement and every minor bumper impact. The potential outcomes of this massive blind spot in consumer protection are staggering, pointing toward a future where the deadliest crashes are caused not by a lack of safety technology, but by the silent, catastrophic failure of neglected digital systems that drivers implicitly trusted. But as terrifying as this digital decay may seem, the automotive industry is already engineering the next monumental leap in highway safety to bypass the limitations of individual vehicle sensors entirely. What happens when your car stops relying solely on its own cameras and radar and begins actively talking to the vehicles around it, the traffic lights above it, and the very asphalt beneath its tires? The era of isolated individual safety is rapidly coming to an end, and the dawn of the interconnected, hive-mind highway is about to fundamentally rewrite the rules of human transportation in ways that border on pure science fiction. The fundamental limitation of every single advanced driver assistance system we have discussed thus far, from the high-resolution stereoscopic cameras to the frequency-modulated millimeter-wave radar arrays, is that they are entirely bound by the physical laws of line of sight. If a massive, solid object blocks the visual or electromagnetic path, the sensor is completely blind. A radar wave cannot bend around a brick building, and a camera cannot see through the solid steel trailer of an 18-wheeler. To shatter this physical barrier, automotive engineers in the year 2026 have successfully commercialized and deployed a technology known as vehicle-to-everything communication, commonly abbreviated across the industry as V2X. This represents the ultimate paradigm shift in transportation safety. We are moving from vehicles that independently observe their surroundings to vehicles that actively converse with the environment, creating a continuous, invisible dialogue that detects catastrophic threats long before they ever enter the physical line of sight. To understand the sheer computational magnitude of this dialogue, we must first examine the core component known as vehicle-to-vehicle communication, or V2V. Inside modern vehicles rolling off assembly lines right now, dedicated hardware modules are continuously operating on the 5.9 GHz spectrum, a dedicated slice of radio frequency heavily regulated by the Federal Communications Commission specifically for intelligent transportation systems. 10 times every single second, your vehicle broadcasts a highly encrypted digital packet called a basic safety message. This localized digital pulse contains your exact global positioning coordinates, your current heading, your precise velocity, the rotational angle of your steering wheel, and the exact state of your braking system. Simultaneously, the vehicle is listening for identical messages from every other V2V-equipped machine within a 1,000-foot radius, forming an ad hoc, decentralized mesh network that physically moves down the highway with you. Let us examine a highly specific case study analyzing urban intersection fatalities. Imagine a driver named Marcus, navigating the dense concrete corridors of downtown Seattle in the year 2026. It is pouring rain, severely degrading optical camera performance. Marcus is approaching a complex, four-way intersection completely bounded by towering skyscrapers that extend all the way to the sidewalk. These concrete monoliths create an absolute physical blind spot. Approaching from the perpendicular cross street, completely hidden behind the corner of a building, is a heavy delivery box truck whose driver has suffered a medical emergency. The truck is accelerating toward a solid red light at 45 miles per hour. Marcus has a green light. His forward-facing radar shows a completely clear intersection. His cameras see green traffic signals. If Marcus relies purely on line-of-sight sensors, a devastating right-angle collision, known colloquially as a T-bone crash, is an unavoidable certainty, bringing catastrophic potential outcomes for side impact intrusion. However, Marcus is driving a vehicle fully integrated into the V2X ecosystem, and the delivery truck, despite its incapacitated driver, is still broadcasting its basic safety message. Before the front bumper of the runaway truck ever breaches the intersection, the radio waves effortlessly penetrate the glass and physical space around the corner. Marcus's vehicle receives the data packet, and the onboard sensor fusion computer runs a complex trajectory algorithm in a fraction of a millisecond. The algorithm mathematically recognizes that the physical coordinates and velocity of the truck will intersect with Marcus's intended path at the exact center of the intersection in 1.2 seconds. Even though Marcus cannot see the truck, and his radar cannot detect the truck, his vehicle instantaneously triggers an aggressive automatic emergency braking event. The car violently hauls itself to a stop just inches before the crosswalk. Half a second later, the massive delivery truck blasts through the red light directly across Marcus's nose. The collision was completely neutralized by data, saving Marcus from a high-speed impact purely because the machines were talking to each other through solid walls. But the hive-mind highway extends far beyond just vehicles talking to vehicles. The secondary architecture is vehicle-to-infrastructure, or V2I. Municipalities across the United States are currently retrofitting traffic lights, toll booths, and active construction zones with dedicated short-range communication transponders. Historical trends have shown that the dilemma zone, which is the physical area where a driver must suddenly decide whether to slam on the brakes or speed up to beat a yellow light, is the primary catalyst for devastating rear-end collisions at urban intersections. V2I completely eliminates the dilemma zone through the continuous broadcasting of signal phase and timing data. As you drive down a smart corridor, the traffic lights are beaming their exact timing schedules directly into your dashboard. Your vehicle knows precisely down to the millisecond when the light 2 miles ahead will turn red. The adaptive cruise control utilizes this data to imperceptibly adjust your throttle, establishing an optimal approach speed that guarantees you will hit a continuous wave of green lights, effectively neutralizing the stop-and-go friction that causes urban wrecks. If a highway bridge ahead begins to freeze, microscopic sensors embedded directly into the asphalt broadcast a localized friction warning to your vehicle, allowing the electronic stability control to proactively adjust the torque vectoring algorithms before your tires ever touch the black ice. The environment itself has become an active participant in your survival. Yet, as we integrate millions of 2-ton kinetic machines into a massive interconnected wireless network, we open the door to a terrifying new vulnerability that engineers are desperately fighting to secure. If your car is programmed to automatically slam on the brakes because it receives a digital message warning of an impending collision, what happens when that data is no longer trustworthy? What happens when a malicious actor, a state-sponsored hacker, or an organized criminal syndicate realizes they can digitally spoof a basic safety message? Imagine a scenario where a hacker broadcasts a fake, digitally forged 10-car pileup on a congested suspension bridge during rush hour, tricking thousands of vehicles into triggering simultaneous automatic emergency braking, paralyzing a city's infrastructure without firing a single physical shot. The potential outcomes of a compromised V2X network are catastrophic, shifting the realm of automotive safety from mechanical engineering directly into the shadowy theater of cyber warfare. The algorithms have saved us from the physical elements, but how do they defend against a weaponized digital assault? This invisible battleground, the cryptography protecting your steering column, and the elite teams of white-hat hackers currently trying to break into your vehicle's central nervous system, is a mind-bending reality that we must completely unravel in our next masterclass.